All right, MSDOSX, welcome back for bonus lecture number 2. Today we're going to talk about Grand Central Dispatch, which is a really cool parallel processing framework available for OS X and for iOS. It's been available on OS 10 since Snow Leopard, and it's been available on iOS since iOS 4. It uses this pretty unique task-based, dispatch queue-based parallelism paradigm. Under the hood, it uses the thread pool paradigm. And it allows you to do synchronous and asynchronous execution. And what's kind of neat is that it abstracts away all of the underlying threads that it processes on. So you no longer have to write that overhead code of creating threads, starting threads, and closing down threads. It handles all of the threads for you, and you just give it jobs you want to do, and it runs them for you. All you have to do to use GCD is just to import the header dispatch.h, and then you have access to all of the functions defined there for doing GCD. So GCD programs divide their work into what they call tasks. A task can really be anything you want, but in general, the idea is it's some kind of unit of operation that your application needs. So it might be performing some computation, it might be modifying some data structure, it could be reading something in from file, writing something to file, and so on. Just kind of one sort of logical unit of execution is a task. And typically they need to be things that can be run safely in parallel, so that way there's no data collisions among them. And you take these sections of code and put them in either a function or a block, which we talked about blocks with core animation, but I'll talk about those again as a refresher a bit later. And then kind of the crux of GCD is that it uses a number of what they call dispatch queues to manage these tasks. All of these dispatch queues are first in, first out. That means you just throw them into the queue. They get, at the very least, they'll get started in first out, first in, first out order. They may finish in a different order depending on how long they take. And there are 3 flavors of dispatch queues. There is a serial queue, there are concurrent queues, and there is one main dispatch queue. And I'll talk about those in turn. So serial queues are pretty straightforward. They execute tasks one at a time in order. So these are just really simple first in, first out queues. For efficiency, the task that's currently running is run on a separate thread. That thread is managed by the queue. You don't have to worry about it. It's just and the one key point is that the thread that the current task of that queue is running on might change between tasks. It's not necessarily the same thread every time, because it just grabs from this pool of threads and just grabs the next available thread, the next one that's based on thread scheduling, which one's going to be run next. And serial queues are really useful for when you need to synchronize access to a resource. So if you have a bunch of threads potentially that are going to be reading and writing to the same data, you probably don't want them to be doing that in parallel because somebody's going to get out of sync. But if every access to that data is put inside of a serial queue, then they're forced to be done one at a time and in order. So that's a really great way for you to synchronize access to some of your data. You can make as many serial queues as you want. One key point is that each serial queue operates concurrently with respect to any other queue. But it itself is guaranteed to be done in serial order, but with respect to any other queues, this includes other serial queues, other concurrent queues, it operates concurrently with them. And the order, therefore, is not defined with respect to other queues. A concurrent queue will execute one or potentially more tasks at the same time, depending on current available resources. Tasks are started in first in, first out order, but they may finish in a different order based on how long they take. And each task that's currently being runs on a separate thread. Again, that thread is managed by the queue itself and pulled from this pool of threads that GCD manages. Unlike serial threads, you cannot create concurrent threads. There are 3 that GCD provides for you, and they do this primarily for efficiency reasons. There are 3 different queues that have 3 different priorities, and you just add tasks to these queues, and it takes care of it for you. If it had to balance a lot of concurrent queues, then that would be a lot of extra overhead and thread dispatching that it wouldn't want to deal with. So if you just keep it in these 3 queues, separated by priority, then it is pretty efficient. And then finally, there is the main dispatch queue, which is a globally available serial queue that executes on the main thread and kind of tries to interleave as best as possible the tasks on it and any other application events. This includes user input, for example, any I/O requests, all these kind of, they're all interleaved so that way there's to keep things as efficient as possible. It's typically used as a point for synchronizing your entire application. So if there's distinct stages the application needs to go through, it makes sense to synchronize those all through the main dispatch queue to kind of make sure that everything goes in sequence in your application. Okay, so some of the benefits, again, just kind of highlighting some of the benefits of dispatch queues is that you're no longer concerned about making threads and starting threads. You just can really focus on what tasks need to be done. And one other nice thing is that behavior is very predictable, well, somewhat more predictable with these queues because they have very well-defined behavior. So that way you can know for absolutely that everything in a serial queue will happen in order. And these are the queues make parallel programming a lot easier because if you've done any parallel programming before, then you know that, for example, when you have shared data, you have to write some sort of locking mechanism to make sure that only one thing can access that data at a time. With a serial queue, it does it for you. You don't have to worry about making a lock because the serial queue is, in a sense, already locked because it only allows one task at a time. And it's actually pretty efficient because they use, I still don't quite understand how it works, but they use a software semaphore, which is basically like a generalized lock, that very infrequently needs to trap down into kernel mode. So it actually stays in user mode very much of the time. So it can actually run pretty quickly and not have to go through the overhead of trapping into the kernel to actually handle the lock. I don't quite know how they did that, but so the locking mechanisms in GCD are actually really efficient. Okay, so in case you weren't here on last time, I'm going to talk again about what a block is. Essentially, a block is a closure. It's a lambda in some sense. It's this pretty neat object-like data structure that the compiler creates and manages. It lives on the heap just like an object. And what's really cool about it is that it can use and access variables outside its own lexical scope. So if it's defined inside of a function, it can use any of the local variables of that function. If it's defined inside of a class, it can use all the instance variables of that class. And those are all bound at the time that code is run. So here is an example block from Apple. We have two global variables out here, x and y. And we have this block declaration. So I'm going to go through the pieces of this because the syntax is kind of funky looking if you haven't seen it before. So you start with the return type of the block. So in this case, this block doesn't return anything. So we'll just say it's a void. And then in the first set of parentheses, you start with a caret symbol indicating that I'm declaring a block. And then you give it the name of the block that you want to declare. And then in a second set of parentheses, you put a comma-separated list of types. No variable names, just the types. So that way it can verify the type signature of the block. So that way it knows what the type of the block is in some sense. And verify that the parameters are typed correctly. And then on the right-hand side of the equal sign is what's called a literal block, where you first, again using the caret to denote that I'm declaring a block here, you indicate a list of parameters and give them names, and then inside of curly braces, the content of the block. Any questions about that syntax? And so notice here that inside of this block, Z is the parameters of this block, but we can also use X and Y, which are, again, defined outside of the block. And those are bound at the time that this code is run. So when we call the block with one parameter, and that's 7, 8, 9, we can still get 1, 2, 3, and 4, 5, 6, because we know what X and Y are. Does that make sense? Okay, so how do we make dispatch queues? For concurrent queues, since you don't need to make one, you just have to ask GCD for it. There are like I said, there are three priorities of a queue. There's high priority, low priority, and default priority, which is somewhere in the middle, I would assume. I think since Lion, there's a fourth one that's background, which is used for when your application is currently inactive and everything else is done. You might want to check the docs for that, though. I'm not positive about that one. But there's a C function, dispatch get global queue. You pass it one of three different pound defines, either priority default, priority high, or priority low. there's this funny parameter 0, which is always 0. Apple has said that they have reserved that for future use. So for now, it always has to be 0. I guess they'll use it for, I don't know what they'll use it for eventually, but it's just it'll make backward compatibility easier when they decide to actually make that do something. And then the type of that is a dispatch QT. And serial queues, on the other hand, you can make as many of them as you want and have them all run independently and in parallel. So the way you create them is you use the function dispatch queue create. You give it some identifier for this queue. It can be, it's a string, so it can be whatever you want it to be. And then again, there's this extra parameter that is reserved for future use that you pass in null. And I think it will cause an error at this point if you don't pass in null. And like I said, serial queues are typically used for, according to Apple, they say that a serial queue should have some specific purpose. Typically, that's protecting some resource. But it can be, the idea is that they don't recommend making a serial queue and then having a bunch of things use it. It should be kind of there should be one use for the serial queue. I have one serial queue for doing reads to disk. I have one serial queue for doing accesses to this variable, for example. They don't recommend intermixing them because then that gets complicated and hard to follow, I think. Okay, so now we have queues. There's also a method for getting the main dispatch queue if you need it, but it's just it's just like getting the concurrent queues. You just ask for it. So how do you add tasks to a queue? So there are 4 dispatch async there are 4 methods starting with the word dispatch that allow you to add a task to a queue and let that task run either asynchronously or synchronously. And there are 2 flavors of each. There's dispatch async will take a block and dispatch it asynchronously. Dispatch async F takes a function pointer, if you would rather use a function pointer than a block, and dispatches that asynchronously. Dispatch sync takes a block and dispatches it synchronously. And dispatch F takes a function pointer and dispatches it synchronously. So here's Apple's example of using both of those. So we create, in this case, we create a serial queue, and we first add an asynchronous task that prints do some work here, and with that immediately will fire off that task or throw it into the queue, and then it may get run immediately or it may get run in a little bit. So this next printf, where the first block may or may not have been run yet because we ran that asynchronously. The idea is that this async function call, this call will exit immediately, and then the block will get run sometime later. You don't know when, but it will get run eventually, just sometime later. Dispatch sync, on the other hand, that function call will block until that. Double uses the word block here, but that function call will stall until the block you pass in has actually completed, and then at that point you know it's finished. I can move on. So at this point, at this final printf, we know for a fact that both have been finished because this one got added second, and therefore it must have been started second. Therefore, once this one ends, they've both been done. Apple highly recommends that you use async as much as possible, just because mostly for efficiency reasons, I think. And it makes your code a little bit cleaner, just to be able to kind of run them and then have the clean solution. The main reason you want to do asynchronous is suppose that block needs to return some value, and you need to get whatever that value the block computed. Apple's suggested cleaner way to do that is inside of the block have a function, have like a callback that calls some other part of your code when it's done. So that way you don't have to wait for that thing to be finished. You can go start something else if you want, and then when it's done, it will let you know with a callback. Yeah, polling versus interrupts. Okay, one last little neat thing that you can do with GCD is you can kind of do a map. So this is a fairly common thing is to loop through a bunch of is to do a loop a bunch of times and do some action in that loop, and it's often the case that each iteration of the loop really doesn't depend on what happened in the previous iteration. So you could very well do them in parallel, and given what you guys know now, that would be that would actually be a sort of a pain to write, because you'd have to make a block for each iteration and queue each block and then let them run. GCD provides a function apply that basically allows you to specify what happens at each iteration, and it will copy that block as many times as it needs and pass it in each increment of the loop variable. And it will do this, and you can do this, and ideally you'd pass this into some concurrent queue, and then it would just let them go crazy and let them all run at the same time. So here we grab one of the global queues, we just get the default priority one, and then so this loop starts at 0, goes up to count, and increments by 1 every time. The important thing is that the way apply works is loops always start at 0, always go up by 1, and stop at whatever you pass in as the first parameter. So if your loop takes other numbers, you have to do the conversion of the math yourself because it will always do it incrementally. But yeah, so it takes in what the max number is, the queue you want to enqueue it on, and then this block that takes as a parameter the index for at that particular the index for that particular iteration of the loop, and then the block for what to do at each iteration. Okay, so that's kind of a high-level overview of what you can do with GCD. Obviously, there's a lot more. Apple's concurrency programming guide is a really great resource for how to write concurrent programs, and especially this page of how to play with GCD. There's a lot more detail that I kind of skipped over because it's complicated. And if you need the reference for all the GCD functions, they're available here. And again, if you want a review on how to use blocks, I provided a link there at the bottom. Any questions about GCD? No? You guys want quiet? Okay.